Hey everybody, I did a little bit more in chapter 6, and I thought I'd set you up to try a few problems before Wednesday. I said that I'd put a schedule together. I think I'll have to work that on tomorrow on Tuesday, and I'll get that to you when I can. In section 4, we want to take what we learned about partial molar quantities and extend it into more realistic situations. And the idea of what a chemical potential is was something really important in 6.2 and 6.3. The idea that the driving force for something happening is the Gibbs free energy. Just because something's in a mixture, we're still going to use Gibbs free energy as the criterion for spontaneity. So as we're setting up here, let's look at the liquid phase and some of the things that can come out of that. So I have a little sketch here. I said, first consider a pure solvent. Whenever you have an equilibrium, the chemical potentials must be the same for both sides of the equilibrium. You might recall that test question when I said an ice cube floating in water. If it's at 32 degrees, that state will go indefinitely because the water that's in the solid state has exactly the same Gibbs free energy as the water in the liquid state. So there's no driving force to go one way or the other. Here we have a pure solvent trapped in a container, and of course some of the molecules will break free and go into the vapor phase. Even though there's a lot more molecules in the liquid phase, we say that the chemical potential of the molecules in both phases has to be the same. It's kind of the definition of equilibrium. So that's what we have here. The chemical potential, which we know is related to the Gibbs free energy per how much stuff you have, in the liquid phase is going to be the same as it is in the gas phase. Now the gas phase chemical potential, or the gas phase molar Gibbs free energy, is going to be whatever it is in standard conditions plus a correction term. This correction term takes account for the fact that when gases are at higher pressure, they have higher chemical potentials, and when they're at a pressure lower than the standard pressure, they have lower chemical potentials. So for a two-component mixture, the chemical potential for each component still must be equal in each phase. So as you can see in my little sketch here, even though I've introduced liquid number 2, it shouldn't affect the fact that if this is an equilibrium, the chemical potential of component 1 is going to be the same in the liquid phase and the gas phase. So that's what I have written here. The chemical potential of component 1, just because it's part of a mixture, still has to be the same as its chemical potential in the gas phase. And as we expressed a little earlier, we could say that it's going to be some variation, depending what the pressure is, from its standard state. Well, what I've done next is combine equations 613 and 614 and make a substitution and get this final expression here that says that the chemical potential for component 1 in the liquid phase is going to be its pure liquid phase chemical potential plus a correction term, which is basically proportional to its mole fraction. If you take a look at that, it's the partial pressure of component 1 in the gas phase compared to the partial pressure when it's in the pure phase, when it's a pure solvent, I should say. This relationship that the partial pressure of component 1 having a mixture, in a mixture I should say, is exactly proportional to its mole fraction is an example of Raoult's law. Now this is only true for some solutions. We'll get to the ones that deviate from that in a minute, but I'm sure you've seen Raoult's law when you learned about distillation in organic chemistry. If you substitute this relationship into the equation on the previous slide, we get basically the fact that the chemical potential of component 1 is going to be equal to the pure in relationship to the mole fraction of that component. Now, solutions for which this is true across all combinations of component 1 and component 2 are said to be ideal solutions. That is, what we see is that there's the delta H of mixture is equal to 0 and the delta V of mixture is equal to 0. Basically, these two components, intermolecular forces, are so similar that their intermolecular forces is nearly identical to the same as the average between AA intermolecular forces and BB intermolecular forces. Make sure that you look at that carefully. It's that the AB intermolecular forces are the same as the average intermolecular forces between AA and BB. So the AAs and the BBs might be different, but it has to be that the AB is close to the average. Well, this is what you see for ideal solutions. And here we have a benzene toluene graph that shows that based on the mole fraction here of benzene, the sum of the individual partial pressures is going to be exactly what the partial pressure of the mixture is. If you have 99% looks like toluene here, well then 99% of the total pressure is going to be responsible. 99% of the partial pressure of toluene is going to contribute to the total, and only 1% of the partial pressure due to benzene will contribute to the total. So let's just do an example that brings into account Raoult's law to see what kind of information you could get out of it. So I have an example here that pure liquid A has a partial pressure of 66 torr, and pure liquid B has a partial pressure of 88 torr. I shouldn't say partial pressure, I should say vapor pressure at 45 degrees. Now what if you make a mixture of these two liquids that's a mole fraction of 0.36 in component A? What's the partial pressure of each component in the mixture, and what's the mole fraction of the vapor? So you're going to use Raoult's law and the definition of partial pressure to figure this out. So Raoult's law is telling us that the mole fraction of A times its pure vapor pressure is going to be equal to its partial pressure. So liquid A is contributing 23.8 torr to the vapor space above this liquid. For the partial pressure of liquid B, I need the mole fraction of B times its pure vapor pressure, and I get 56.3 torr. So the total vapor pressure above this solution is going to be 80.1 torr with these two partial pressures. If you want to know the mole fraction of each component in the vapor, you need to take its partial pressure over the total. So the partial pressure of A over the total will give you the mole fraction in the vapor phase. For B, the partial pressure of B over the total gives its mole fraction. So again, as you learned in organic chemistry, I'm sure this is a good review, the more volatile liquid ends up enriching in the vapor. And so as you do this, you could purify your compounds by doing repeated separations this way. So most solutions, however, are not ideal. Here we have what's called a positive deviation from Raoult's law and a negative deviation from Raoult's law. Look at this mixture on the left. Carbon disulfide and acetone has a positive deviation from Raoult's law. What this means is that the mixture is going to have a much more volatile vapor than you would have predicted if it was ideal. What this basically means is that the intermolecular forces between carbon disulfide and acetone are really pretty weak, so that these molecules would rather be in the vapor phase than stuck in the liquid phase. And so you could see this positive deviation. What if the new component, in this case I have chloroform and acetone, what if their intermolecular forces are stronger than the average of the two pure solvents? Well, then you see a negative deviation. Basically, the vapor pressure of this mixture is less than you would have predicted just by adding up the values that you would have gotten from Raoult's law. Now, just because these curves end up being something other than straight lines, it doesn't mean that they're completely useless. Let me show you. First of all, note that the Raoult's law can apply if one of the components is in a large excess. So what I did is I abstracted, or these two figures abstract two of the lines from the previous page. You could see, for example, that if you look at the carbon disulfide line from the left-hand graph earlier, you could see that the end point, let's say it's something like a 0.95 and above mole fraction in carbon disulfide, does follow a linear relationship to Raoult's law. And so you could use Raoult's law if the acetone was only a small contributing solute. Similarly, over here, where we had this was chloroform with acetone, and I noticed the mole fraction of acetone is the scale here. Notice that maybe for the range about 0.9 mole fraction and above for the chloroform, you could use Raoult's law. So that would be fine. Something interesting happens, though, with solutes that deviate quite a bit from being an ideal solution. They still follow a linear equation, and that's what I have written here. Components in small amounts can obey a linear equation with not the pure vapor pressure like Raoult's law, but something called the Henry's law constant. So what this is saying on this equation here is that the partial pressure of component 2 is going to be proportional to its mole fraction times K, which is this Henry's law constant. So if you take a look at an example here for the carbon disulfide, if the carbon disulfide is roughly between 0 and 0.1 mole fraction in acetone, which is what this curve is for, you can use a linear relationship if you know the value of K. And notice that the value of K is going to be basically the extension of this line all the way with the right-hand part of the axis. So it's going to be something very, very different than the pure vapor pressure, but it's still a linear relationship and it can give you good information. Over on the right-hand curve, you could see that for the chloroform, there's actually a pretty substantial range of mixtures for which you can get a linear relationship. Basically, up to about a mole fraction of 0.25, you can get a linear relationship knowing the Henry's law constant, which again is going to be the intersection with that graph. Usually you look these up in tables, though. And I have an example for you on the next page, and you could practice some of these with the homework that I'll assign. Two of the lines. So Henry's law, remember, it's only going to hold for dilute solutions. Another thing that you notice, if you look at the table in the textbook, table 6.1, you're going to see some very large differences in what these Henry's law constants are. One thing you'll notice if you look carefully is that some gases have very, before I get into gases, I should mention, even though the examples I just showed you on the previous slide were for liquid mixtures, you could also use Henry's law constants. In fact, they're probably used the majority of the time in chemistry if the solute is a gas. So they do hold for gaseous and liquid solutes in a solvent. So here I see carbon dioxide, hydrogen sulfide, ammonia, and HCl. All four of those gases do interact somewhat chemically with water as a solvent, and so you're generally going to have high solubilities for those gases compared to something like nitrogen or helium, which don't interact, and they're going to have really low solubilities. But let's take what we've learned and try to use a Henry's law constant in an expression in an equation that might be of interest. So calculate the mole solubility. They do pick mole for a reason. A mole solubility of carbon dioxide in water. I noticed that the value they use is 3.3 times 10 to the minus fourth atmospheres for the partial pressure of CO2. Some of you may know that due to global warming, or really for burning of fossil fuels, 400 ppm is basically the actual concentration in our atmosphere. But let's just take the numbers they gave us and figure out the mole solubility. So what I did is I took a look at the Henry's law equation and I rearranged it. So you can see that the mole fraction of the CO2 is going to be the partial pressure of the CO2 over the Henry's law constant. Now, how do you know what the mole fraction is? Well, it's going to be the moles of the CO2 over the moles of CO2 plus the moles of water. Notice that this problem we're going to assume 1 kilogram of water, and if you do that, you realize that this is such a small solubility that I could eliminate the moles of CO2 in the denominator, and get this expression for the mole fraction. So if I take this expression and substitute it into the Henry's law equation, I get this equation right here. So the number of moles of CO2 that are dissolved in the 1 kilogram of water will give us the mole solubility. So I take the partial pressure and I convert to the correct units. I notice that the constant, what am I doing here? The constant is in torr, so I basically took my atmospheres and converted it to torr. Then I have the moles of water, and then I'm going to divide by the Henry's law constant, and I get a value of 1.12 times 10 to the fifth moles, minus fifth moles, which also, because we're dealing with 1 kilogram of water, is 1.12 times 10 to the minus fifth mole. Alternatively, you might have noticed that in table, again, 6.1, there is this K prime Henry's law version of the constant, and this is more direct, but you get exactly the same number. I found 5 problems that use some of the things in this section and the section prior. Why don't you give those a try for Wednesday, and we can go forward. I might put up something else tomorrow, and also keep an eye on. I have in mind your schedule for PChem and seminar. I talked to a couple of the professors already, and we should be all set to go with that. All right, take it easy. Hope you're doing well.